Okay, because it's there, a bit of a cheesy title today. I don't know if I like this title very much, but whatever. It is what it is. Okay, we're going to be looking at a certain uh, pair of categorical structures today, namely adjunctions and monads. And these are a little bit difficult to motivate, but it's clear that there's structure that is there, hence the title. So I'll start with a motivating example, and then we'll get into general definitions, and then some more examples. That's going to be adjunctions, and then adjunctions naturally give rise to monads. So that's going to lead into the next part of the talk. So the goal today is adjunctions, and then monads. Okay, so the motivating example is just a neat little relationship that you can find between the category of sets and the category of complex vector spaces. So if I had a set, so let S be a set, then I can consider the complex vector space, which is freely generated by S, and I'll define this. So definition, the complex vector space, underline this, generated by S, denoted CS, has, and so the elements are just formal finite sums of just products of the complex numbers with this set S. So you read that formally. So let me write down an example. Elements are finite formal sums Z1 S1 plus dot 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 plus Zn Sn, where n is greater than 0, Zi is an element of the complex numbers, and Si is an element of S, and that's for all I, equaling 1 up to n. Okay, so you pick a natural number, and you take a collection of these elements inside S, and then you pick n elements of S, and then you take a linear combination of such a thing with complex numbers, and that gives us one element inside this vector space. And then the collection of all such things gives us the total set. And then scalar multiplication is defined as follows. So I can write this down explicitly. C times CS to CS. It's just the way that you would expect it to be, given the way that I've suggestively written the elements. So if you give me an element Z, and you give me a sum from I equals 1 to n of Zi Si, then this maps to the sum from I equals 1 up to n, Z times Zi times Si, right? And then notice that this happens inside the complex numbers, right? So therefore you can go ahead and perform that multiplication. So that is not a formal multiplication. That's a genuine multiplication inside the complex numbers. Okay, and then addition is performed by gathering like terms. So I'll just write that down. Gathering like terms. So you have two different formal sums, and there might be an intersection between the elements of S in one formal sum and the elements of S in the other formal sum. If that happens, then you can just add together the coefficients in front of those in front of that common element, and that addition can be performed inside the complex numbers. So again, that's not formal. You can genuinely perform that addition. Okay, and that gives us a complex vector space, but there's a bit more that can be said here. it's more than just from a set I get a complex vector space. It's actually that a lot of the structure of this complex vector space is given by the structure of the set S. So let me make that a bit more precise. There exists an obvious map, just an inclusion from S into this complex vector space. Call it iota maybe, from S into CS, and why wrote the C there. And the elements in the image of this map form a basis for this vector space. And by the way, we identify the elements in the image with S itself. Okay, so the structure that is determined for this vector space via S comes down to the morphisms inside the two respective categories, right? So S is a set, so we can look at set functions on one hand, and then CS is a complex vector space, so we can look at linear transformations on the other. And a lot of the structure of the linear transformations is given by the structure of the set valued functions. And you can see that via a very simple calculation. So an example of the relationships of the structure between S and CS is given by the following experiment, I guess, following thought experiment, given another complex vector space V and a linear transformation phi from CS into V, then for an arbitrary element of CS, call it Z1, S1 plus dot 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 plus Zn, Sn, we have by linearity that phi of Z1, S1 plus dot 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 plus Zn, Sn is equal to Z1 phi of S1 plus dot 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 plus Zn phi of Sn, right? That's what that means, is that this linear transformation phi is completely determined by its action on these elements inside S. I mean, that's obvious anyway, because of what I said earlier, that S forms a basis for this vector space, CS. Okay, so phi is determined by the set phi S. And then the point to make is that every such natural transformation, every such linear transformation is given in this way as well. So any linear transformation from with domain this freely generated complex vector space is determined by these elements. So it's given by and determined by. So that means that we have a relationship between the linear transformations and the functions outside of, and the functions with domain S. I always have this language from outside of S, and that's not a good way to put it. So with domain S, okay? And even more can be said than that, but let's go slowly. So let me write up what I just said, and then I'll point to it. Okay, so in other words, if we let UV denote the underlying vector space of V, sorry, did I say underlying vector space? Underlying set of the vector space V. Then phi is determined by its restriction. So I just reduce phi to S, and this is mapping from S into UV. And the point is, phi in all of its full glory is a linear transformation. But once I restrict it down to S, I also psychologically just forget that there was ever any linearity involved in the definition of phi. I just think of this as a function between these two sets, right? And so that's a mapping from a linear transformation to a function of sets, right? So I've really, behind the scenes, defined a functor there, but we'll get to that. So the proposition is for any set S in any complex vector space phi, there is a bijection from this Hom set, so the set of linear transformations from CS to V, and this Hom set inside the category of set. So this is functions from S into the underlying set of V. Okay, and even more can be said. So in fact, if F from S to T is a function of sets, and let's say psi from V to W is a linear transformation, then we have commutativity of a pair of diagrams. Okay, and this is the Hom set CS to V mapping into Hom S UV, Hom T UV, Hom C T V. These arrows go upwards because it is a contravariant functor. This is blank comma C F. This is blank composed with F. This is the bijection from above. This is the bijection from above. And then we also have naturality in the other argument. So CS V Hom S UV. These are covariant functors, so this goes down. U W Hom CS W. And this is post-composition. And this is the bijection from above and bijection from above. Okay, so we get commutativity of these two diagrams, and it's an easy exercise to convince yourself of that. And what that is to say is that we have naturality of the above bijection, so this one, in both of the arguments. So it's natural in both S and V. Okay, so that's a little piece. well, sorry, I just heard echo on myself. That's a little piece of structure that exists and it sits there. And we see that there is a strong relationship between the linear transformations that a priori seem to be a restriction. It seems to be a type of function with given restrictions on it. I mean, we have the restriction of linearity, but it's completely determined by just the set valued functions, not on the underlying vector spaces of what we started off with, but between related um, sets, right? So there's really a functor at play here. And in fact, there's two functors. There's the free functor and there's also the forgetful functor. And the point is that they're kind of connected to each other. They hold a relationship from one to the other, but it's not like they're exactly the same thing or isomorphic as functors themselves and things like this. So this is a possibly new type of connection that could exist between different mathematical objects if you haven't seen it written in this category theory language before. And this is one of those instances. We had the same thing in the naturality lecture that we gave, where, is category theory just a language or is it more than this? This kind of structure is very hard to describe if you don't use the language of category theory, but it's not, strictly speaking, necessary for it. Okay, so let me.
Did you say what CF is?
Oh, CF is just the function that's induced by the set F. So if I have CF of Z1 S1 plus dot 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 plus Zn Sn, then that's equal to Z1 F of S1 plus dot 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 plus Zm F of Sn. Sorry, that's an N. So I was saying earlier that if we have a natural transformation, then by linearity, it's determined by what happens on its basis vectors, and this is reading in the other direction. So therefore, if I have a function on the basis vectors, then I can induce a natural transformation from that. Make sense?
Yep.
Nice. Okay, so the definition of an adjoint pair is the following. Let F from C to D and G from D to C be a pair of functors. Then the functor F is left adjoint to G if for all y in D and all x in C, there exists a bijection between these Hom sets which is natural in both x and y. Okay. So if we take C to be complex vector spaces, we take D to be the category of sets, we take F to be equal to U, and this is the forgetful functor. Because you forget the structure. So we start off with a complex vector space, V, and then we just forget that it's a vector space. We throw away the scalar multiplication and we throw away the addition, and we just take the underlying set. And then for the morphisms, which are linear, we just forget the fact that they're linear and take them as set-valued functions. And then we take G to be equal to C blank, which is the free functor. Then we get back the example that I opened up with. With the forgetful functor on the left. Okay, so an adjoint pair is the pair of functors along with a structure, and then there's always a functor on the left and a functor on the right. And we use this turnstile notation to denote that.
You said the left adjoint. What does that mean?
Oh, so adjoints are unique up to unique isomorphism in some correct sense. So, I mean, I still haven't worked out how I feel about this kind of thing. So it's not completely uniquely determined, but it is unique up to unique isomorphism, meaning that if you give me another, say, if f prime is left adjoint to CU or something. Okay, let's work in the general definition. So using the notation of the definition that I gave at the top of the board, if f prime is also left adjoint to G, then there exists a unique natural transformation eta from f to f prime. And I suppose this has to make a certain diagram commute. So what is that? Such that I don't know if I can reproduce this just here on the spot. There's a certain condition that this needs to satisfy, or else it's not uniquely determined. So might have to modulo this. Okay, we'll have to look that up, but I can post that on the Discord once I've got the correct definition. I'd have to either work that out on the spot or guess, and I don't want to get it wrong. So sorry, it's not on the top of my head at the moment. But yes, there is a uniqueness statement that can be made here. Okay, let's move on to the next set of boards. Okay, so as an exercise, I can say find, so here's another example, but I'm giving it in the form of an exercise. Find a left adjoint to the following forgetful functor. There are many, many, many forgetful functors in the world. Here's another one. To the forgetful functor from pointed sets to set, and the category of pointed sets consists of objects x, x, where x is a set and x is an element of this set, and that simply gets mapped to the underlying set. So we forget the elements that we have coupled x to, okay? And then inside this category, a morphism from x to y is a function f from x to y such that f of x equals y. Okay? And then again, this will just be mapped to the function f. So we just forget the fact that it satisfies this property. Cool. So I basically did all of that in order to get to monads. Monads is a thing that I'm slightly more interested in because I got interested in these from the category, sorry, not from the category theory, from the computer science perspective many, many years ago. And adjunctions and monads arise naturally in mathematics, but I first got into them via the computer science perspective. So I'm going to give the mathematical definition and the mathematical presentation of monads today. And then next time, which is going to be after Christmas, so sometime in the new year, I'm going to talk about how monads are used in computer science, both in theoretical computer science, but also in practical programming language design. Okay, so let's look at the definition of a adjunction pair and then think about it from a certain perspective. So an adjunction is a pair of functors f from C to D and G from D to C, satisfying some conditions, right? Satisfying ... So what we can do is we can say, okay, there are kind of two different sides of this pair. There's the side on the category C and there's the side on the category D. So we can say how much of the adjunction can you see from just one side of the adjunction? Let's take a particular side. Let's take C. So I'm speaking informally here. Okay, how much can we see from C? Now, to begin with, we can definitely see one of the composites, right? So if I do F after G, then this is now a functor, which is an endofunctor on C. This is mapping from C to itself, right? Okay, so we can see that. What else? Well, let's assume again, as we have been, that F is the left adjoint to G, and then recall that we have this this natural bijection of Hom sets fx y to Hom c x g y, and then we can notice that we can notice that this natural bijection holds for all objects y inside the category D, right? So in particular, we can set y to be f of x, right? And then one side of this bijection has a special element inside it. So Hom fx is in bijection with Hom x g f x. Okay, and this has the identity element on fx inside it. And so that maps to some special element. We're going to call this eta sub x. Okay, and if you take all of those together, so the collection of all of the eta x's ranging over all x, then that in fact pieces together to a natural transformation. So eta being the set of all eta x for x an element of C is a natural transformation. And moreover, it's a natural transformation between endofunctors on C, right? So let me write that on the next board. So eta maps from the identity on C to GF or FG? GF. GF. And these are both endo functors on C. Okay, so we're going to count that as something that C is able to see, right? Now, if we go back to this natural bijection of Hom sets, we can do a very similar thing because we're also able to range over all X inside the category D. So when we took Y to be equal to Fx, we could also take X to be equal to GY. And a very similar thing happens. So we get Hom FGY, comma, Y, Hom G, Y, G, Y. And then there's the identity on GY inside this set, and this maps onto something. We're going to call this epsilon Y. And then we have a similar statement that the collection epsilon, which is all of the epsilon Y's ranging over all Y, an element of D. Wait, did I get that right? Yes, in D, is a natural transformation. And this goes from Fg to the identity on D, right? But the quote unquote problem, it's not a problem at all, but with our idea of thinking about what can one side of the adjunction see, we notice that this is a natural transformation between a pair of endofunctors on D. Okay, so that's not quite inside the sight of C. But what we can do instead is we can just always consider G, wait, there isn't G, it's F. F, we can consider F of Y for all of these Y's inside D. Wait, hold on, does that make sense? No, we can consider F of X for all of the X inside C. So what we do is given X inside C, take epsilon of Fx, which is going from Fg, Fx to Fx, and that is a morphism inside D, and so then we can apply G to this. And we get G epsilon Fx goes from G F G Fx to G Fx. And then this is also a natural transformation. So we'll call it G epsilon sub F, and it goes from GF, GF to GF. Okay, and this is a natural transformation between a pair of endofunctors on C. Okay, so to summarize, what we can do is take M to be equal to this composite GF, which was the original endofunctor on C. And then I'll write mu for this natural transformation that we came up with as well. Then what we have is the following data. A functor M and a pair of natural transformations. Eta from the identity on C to M, and mu from M squared to M. Okay, that's the data of what we were able to obtain from the adjunction pair. But we actually have a pile of conditions that this data satisfies because we haven't used all of the structure that the adjunction admitted. So in particular, we haven't used naturality of the bijection inside the isomorphisms. Well, I guess we did in part in order to get that these were natural transformations, but there's still more that you can get. And so we can now give the general definition of a monad. So a monad is the data of the above, but I'm going to write the conditions that it must satisfy. A functor M from C to C. Have natural transformations from the identity. Oh no, my pen's misbehaving. Identity to M and mu from M squared to M. Thank you to the ghost who is erasing my pen drops. Satisfying commutativity of the following. And you want to think about these as multiplication and unitarity. Okay, so think of mu as a multiplication, think of eta as defining an identity, and then these conditions will tell you that they behave like such. Okay, so this is t applied to mu, and this is mu, so sub t. So that's all of the that's all of the morphisms that are given by the natural transformation, where I only consider objects which are t of something. And then upstairs is just take all of the natural transformation, to all of the elements of the natural transformation, and then apply t to it, a t to them. And then here is just mu and mu. So we ask for commutativity of this diagram. And then t maps into t squared via eta. So I think that looks a bit like a mu. That's an eta. And then this is eta sub t. And this multiplies down into t. And we ask for equality here. So that can be replaced with the identity morphism if you want. Okay. And there is an appropriate sense in which this is just genuinely a monoid, right? So you can think about this as associativity and this as unitarity, as I already mentioned. And so this is just an associative monoid inside a particular category, and it's the category of endofunctors upon the category C. So it's more than an analogy. This is a monoid. Okay. So I can move on to some examples. Okay, yeah, let's move on to some examples. Yeah, that's almost all.
As in, people say like a monoid is just a monad is just a monoid in the category of endofunctors. Kind of a myth at this point.
I genuinely find that a helpful way of thinking about monads.
Sorry, say that again.
I genuinely find that a helpful way of thinking about monads. That was kind of a funny moment in my education. I remember having that moment where I was like, oh, this literally is just a monoid in the category of endofunctors. And I was like, oh, That's totally a nice way of thinking about it. It really isn't that hard. Depends on what you consider hard, I guess. Okay. There's an exercise. There's an obvious exercise lurking here. Oh, is it? Okay, let's fix that. All right, thanks. Okay. No, I don't know what to say. Obvious exercise. It's not an obvious exercise. There is a good question lurking here, right? The good question is, um, doesn't matter which side of the adjunction that you picked, right? So I said let's focus on the category C and then see if we can extract a definition from that. And we did. We extracted a definition of monads. If you had taken D instead, then maybe it looks symmetric, but it's not because F is the left adjoint, right? So if I took G, then I'm now looking at the right adjoint. And indeed, you do get a difference. So the exercise is look at the definition of an adjoint pair from the perspective of the category D instead, and invent the definition of a comonad. Okay, with that out of the way, we can look at examples of monads. So let's take this endofunctor on the category of sets, which is the list category. So, sorry, the list monad. So it takes A to the disjoint union over all n greater than or equal to 0 of A to the n. And then for all sets A, eta A is from A to TA, and it simply takes an element A and it maps it to the singleton sequence A, right? And then mu is concatenation. Then this is a monad. And in fact, it's the monad that arises from the adjoint pair that we looked at the very start, which is to take the free functor followed by the forgetful functor. Okay, so this is a good example for that reason, but it also gives you a hint as to how we're going to be using monads in order to model notions of computation from computer science, right? So if you wanted to work on the level of sets, but really consider sequences of sets, then this is the monad that you would use. Okay, and that will be made less cryptic next time. So another important example is the maybe monad.
Sorry, could I just ask a quick question?
Go for it.
Looking at mu is concatenation. I'm just backtracking from like our definition of the kind of thing that mu has to be. So on the previous board, you said mu is from m squared to m. It's a natural
Yep.
transformation. What did you mean by m squared? As in
Oh,
the
so
combination?
yeah, that's T applied to T. So it's T composed of T. So it would be T of A. So it's finite sequences of finite sequences of elements of A, right? So it's like this.
Oh, okay. Because I thought when you said concatenation, it would be like a pair of things, and then I thought, say, by m squared, maybe you meant like uh the product of m and m. But
Yeah,
okay, that
so
was
not
like an
quite
opposition.
right. Yeah. So I guess that I don't know how to notate this. So I've unfolded that sequence, and I'll do that for all of them. So think about it as n-ary multiplication, right? So normally when you have a monoid, a monoid, you would think about the multiplication of 10 different elements as kind of you do two of them at a time. So there's implied brackets there, and you multiply these two binary. You do the binary multiplication of these two, and then you get an answer. Then you do the binary multiplication of these two, etc. Whereas here, think about concatenation as multiple multiplication. So you take everything together and you kind of unfold it at once.
Mm-hmm.
Does that make sense? So I'm multiplying all of these elements together in one step, just by concatenating all of the different sequences.
Yep.
Okay. So going back to the example, another important example is the forgetful, not forgetful. God, I get so tired and I should start saying stuff. It's not forgetful at all. This is the maybe monad. Okay, T from set to set. And this maps an object A to a co-product with some formal element. It really doesn't matter what this thing is, but we're going to call it bottom because we're going to imply that this is failure of computation. So this monad could be used, for example, for modeling partial functionality with total functions. So how do I model partial functions with a total function? Well, I just add an extra element and say everything that maps to that I'm going to think about as not having an element in the codomain assigned to what mapped to it. So that's undefined. So the pre-image of, so if this is, forget it. I'm going to talk about that next time. But yeah, we're going to model partial functions using functions by adjoining a formal indeterminate. And then to complete the definition of my maybe monad, we have where eta A is going from A to TA, and it just maps A to A, right? And then mu, so mu A goes from T squared A to TA. And maybe I can spell this out explicitly. So this is going to be a disjoint bottom, disjoint bottom. So for simplicity, let's make that bijective to bottom and, I don't know, bullet or something, right? We're just in the category of sets. So this is really just adjoining two formal elements. And then that has to map to a disjoint bottom. So that's not that style of arrow. This set is mapping into this set, and it does it by A maps to A, and then bottom and bullet both map to bottom. Nice. So this is also a monad. And wait, maybe I haven't checked this, but I believe this one comes from the other example that we looked at that I left as an exercise, going from pointed sets. I wonder if that's true. I'm not sure about that. I think this. No, no. That doesn't make sense because it doesn't compose properly with the forgetful functor. Okay, so yeah, okay. There has to be some functor from the category of sets to the category of sets that just adjoins a formal element, and then there's also the identity functor. And I propose that that's the pair of functors that give rise to this monad, but I guess I haven't checked that carefully enough, so I'm not sure. Okay, that's, I guess I finished early again. That's basically all of the content that I wanted to cover, but I was going to end with just a little bit of an explanation as to why I find monads interesting. So as I said earlier, they are important in mathematics, but they've also been used extensively in computer science. The previous two examples give a hint as to how, they're very helpful for modeling side effects of programs, where you might be working with a programming language that is purely functional, so it's not capable of side effects. So, for example, the untyped lambda calculus or the simply typed lambda calculus or programming languages that have been built off them. For example, Haskell. Now, Haskell does have side effects, but they can be explicitly programmed in by the programmer using monads. So that's a practical example of how monads have been used inside computer science. But you have to massage the definition a little bit to get the properly applied version of it. So there's a little bit of it's not a deep theorem per se, but there's a bit of work to do there to see how the practical version of monads, which is what you get when you look at the Haskell Wikipedia of monads, so the data type constructor monad with the category theory definition, but they are the same thing in modulo some stuff. But I'll explain all of that next time. But for now, I'll leave it as monads arose naturally in mathematics, and then they were used extensively in computer science, both for the theoretical modeling of side effects of programs, but also for the practical implementation of program. They're genuinely used inside certain programming languages. Okay, that's the end of my lecture. I think that the only appropriate thing to do would be to go back and work out the uniqueness statement of adjunctions. So maybe I'll say thank you. That's the end. And now let's move on and try to work out that.
Before we do that, can I be picky about something?
Go for it.
On this last slide, you're talking about like, okay, a disjoint union is just like adjoining a formal symbol. I think talking about formal symbols is fine in the context of, say, explaining what a polynomial is or something, where you're like, there's a particular set, like the real numbers or the complex numbers, and you're not talking about all sets. But when you're talking about the category of sets and you have all sets and all the elements are in play, I think it's kind of nonsense to talk about like a formal symbol that's somehow this like new thing that's not in any of the current sets in play.
Yeah. Yeah. I mean, yeah, so that's what I was going to say. You could put anything here. You could even, if you want to make it dependent on this, so that there's no independent choice of all of the sets, you can even just put A inside there. So it's A disjoint union, the set containing A, for example. Yeah.
Yeah, okay. But that's what I meant uh was that maybe a like because when I say you're using a formal symbol in this context, I'm specifically pointing to the explanation of what a disjoint union is, because when like the alternative, which I think we haven't explained, is that a disjoint union can be modeled in such a way that we don't need to make sure that the extra thing on the right that you're disjoint unioning with is like not equal to any of the elements of A. And then you don't need this mystery of like these having like two formal symbols at the bottom.
Yeah. I mean, this is just a way of thinking about it. So there's nothing wrong with a disjoint union, though. Are you saying that there is, or are you saying that that's how I should have done? I should have specified that. I mean, for instance, this could be the set containing bottom, as I'm calling it. Like this could be a point set, an arbitrary one, and then this maps to this, and that's.
I think it would have been better.
And
Obviously, I think what you said was fine, but I think maybe Billy would have preferred if you had defined the map out of t squared using the universal property of a disjoint union, right? So you could have said, to define a map out of this disjoint union with the one point set, I have to tell you where the one point set goes. It goes to bottom. And then I have to tell you where the other factor goes, and the universal property of that lets me send bottom to bottom and so on. So you don't actually have to introduce a bullet.
I think it's nice to just briefly mention like the two inclusion maps, and then talk about the elements of the disjoint union as like iota 1 of something and iota 2 of something,
Mhm.
rather than forcing the elements of the disjoint union to be literally like containing the elements of A. And then you can like be more explicit about what this map is, this mu A map is, by using those inclusions.
Mhm. So don't forget that one way to realize the disjoint union is by just labeling the different by labeling the elements inside the sets differently and then taking the union, right? And the point is
That's
that
what I'm saying. You're as in labeling by speaking of them as iota 1 of something and iota 2 of something.
yeah, but so that's a more general way of thinking about it, because then I'm looking at the inclusion maps into an arbitrary disjoint union, an arbitrary coproduct, right? Whereas if I were to take the disjoint union in particular, then yeah, I have a particular choice of labeling, and I really specify how I do that.
But
But
like, what do you mean by labeling?
well, I think it does make sense when you've got a particular choice of disjoint union, right? So I could say, I could define a star, maybe stars are bad notation, but I can take that to be the set of all A comma 1, given A is an element of A, right? And so now that's been labeled, the elements of A have been labeled by 1. And then I can take the singleton set bar, well, okay, is this the point? Like, this has been labeled 1 and this has been labeled 2, so maybe you want that inside your notation.
Yeah, I'm just proposing the same thing, but all I wrote was instead iota 1
Yeah,
of
but yeah, iota 1 of A, yeah, sure. That is the same thing where you've taken a particular choice for iota, but don't forget that that's got a
like
particular choice. Whereas
it
what
could
Dan
be,
wrote here was general,
this
right?
choice.
Like using iota, I guess it's equally as general here. The point is, the reason why this laziness is okay is because the only property of the disjoint union that I'm using is the ability to distinguish which set your element is an element of. And we can do that in any realization of the disjoint union. So I am using a particular choice to make this point, but the idea is that it's okay because in the general case, I'm not using anything particular about this one realization. But whatever, like yeah, we can go ahead and write iota 1 of A if you would like to work in that more explicit level of generality. I think that maybe this is probably the best way to do it up here because
Yeah, I wrote what's on the top right to be clear.
yeah.
Because there's also, because there's two bottoms here in the like in T squared A, like
Mhm.
here it kind of, I guess it doesn't matter because they both end up being mapped to the same thing, but maybe in another monad, like they could be mapped to distinct things or something. In which case, like just having bottom and dot as just like two anonymous things, like maybe one of them has a more special role, being like depending on which one it is. Just a thought.
Yeah, maybe, but I think you're gonna not get naturality in that case. I mean, this has to be a natural transformation from T squared. So the point being, I don't think you could dig into here and find the most recently adjoined singleton set. I think I think that would abuse naturality.
Right.
Yeah. And also the fact that it's t squared, right? Like I need to say this is what t is. And yeah, okay. So let's see if I can.
He just left.
Hello again, Will.
Yeah, hey, it's really annoying that I disconnected. So just I don't know how far through that I got, but summarizing the point I was trying to make to Billy is I was saying, think about this diagram that we need to commute as per the definition of a monad, and then think about what t cubed is. T cubed in this case is going to be this thing. So you're adjoining 3 different elements, right?
Mm.
And then let's see if I can color code it. So this guy, what's that doing? That's taking mu, so it's going to perform multiplication to this. Like think of it as multiplication of these 2 elements, and then you just apply t to that entire thing, and then this one here is going to perform multiplication of these 2 elements, and then you just do that to the morphism or the object that has had t applied to it. So in one situation, you're multiplying these 2 elements, and the other one, you're multiplying these 2 elements. That's the whole point. It's meant to be associativity, right? And so in one case, this element here is seen as the element of the monoid on the left. And, I'm speaking informally here. And then in the other case, it's thought of as on the right. So if we dig into this definition and find the most recently adjoined bottom element, and then I do this to it, and then I find the second most recent, and I do this other thing to it, then if they're genuinely different, you might end up violating commutativity of this diagram, right?
Yeah.
Yeah, so maybe there is some example where mu mods out by that difference, but then I feel like that's unlikely because mu is also involved in these 2 maps. So I think it's meant to be a bit agnostic towards which is the first element, which is the second element inside the binary multiplication. And if you think about it, that's kind of what associativity says. So
Just thinking about like working in Haskell, like there's a distinction to be made between these 2 elements before you apply the map mu, like within the language of Haskell. I think sorry, I'm forgetting, do they use the word nothing
what's for nothing?
as in like the extra element, like the bottom element of the
I don't
like
know what Haskell calls it.
okay, well, I think if you have a type A, then maybe A consists of just A, like for
Yeah.
some lowercase a, and nothing.
Oh, nothing. Yeah, that's it. Yeah, that's it.
Yeah.
You're right.
And so there's a difference between nothing and just nothing.
Yeah.
Which is what I'm thinking of, like these 2 different formal symbols. One of them is nothing and one of them is just nothing.
Yeah. So don't forget that there's nothing in Haskell that forces what you've called a monad to be a monad, right? So in particular, these diagrams here, they don't need to commute, right?
What do you mean need to? Like what's
They just might not. You can definitely define a monad where these diagrams don't commute, and Haskell will happily treat that like a monad, right?
okay?
So it's up to the user to decide whether they care that what they're making monads are in fact monads. So if you were programming in such a way that just nothing and nothing were treated differently, then yeah, you might write some brilliant program, but you just might not be using monads, like from the category theory perspective. So who knows what that means, right? And yeah, I think that's the main point to be made when I think so. I'm not entirely sure about it, but when you're describing the difference between computer science monads and category theory monads, I'm pretty sure that's the main point where the
Well, isn't
idea,
that because,
yeah.
like in Haskell that they don't have the like in the standard library, there's no sort of way to express the fact that it's a monad and like force it to be.
Yeah, I mean, it's just not. I thought it was just Haskell trying to be a bit more manual, right? So it's not wanting to jump up at you and be like, "Oh, we checked and this isn't a monad, so you can't write it down." It's like you're allowed to use things that aren't monads as monads.
Well, I think
But
I think
the
it's
main
because
point is that it's not data, right? Like your
mm,
proof that it's a monad, where is that going to go? What is that?
mm,
yeah, like in you need a richer language. I think Lean, especially Lean 4, has like managed to uh obviously it starts as just a completely like proof oriented language. Like the point of it is just to write proofs uh in Lean, but I think they've made it a lot more usable as like a Haskell type language, and while keeping the ability to express properties with the full richness uh, of its like proof system.
okay.
So I think you could very much like do monads in Lean. I'm certain
Mhm.
they've done this, and also express the type of monads or whatever it is, um, specifically such that you can't just express faulty monads or something.
Mhm.
Like the data
Mhm.
includes the proof.
Yeah, yeah, that makes sense for something like lean. Okay, that's interesting. Hey, I've got a question for you. So, since I prepared this lecture for the Paris course, YouTube has been feeding me a lot of videos on monads in computer science. And I've seen a lot of videos that are kind of to the, an example title is Monads are great and they're very beautiful. Now get them out of my programming language, right? And yeah, and other ones like monads are great, but they have this major fallacy. And I remember when Dan and I were talking about this, we had this big conversation about the distributivity law. So monads don't necessarily compose, and maybe that can cause an issue, etc. But I was wondering, like, you know, t- however many years it's been since Haskell has introduced monads, and we've had people inside universities learning it and struggling, etc. Do you know what people's attitudes are in the modern day towards monads inside programming languages, whether it's stood the test of time and seen as, yeah, this really was a good idea, or whether people think that they're not really good enough.
Yeah, I don't think I ever got answer to
Yeah,
that.
that's right. It'd be interesting to
I
see
think
what they're
I
doing.
have seen more generally that uh like there's a sort of generally accepted idea that like functional programming is better in some sense,
Yeah.
and like a lot of people try and push their code in whatever language to be more functional, but for all of the like theory we have and all of the like reasons we have for functional programming being so much better in every way and less prone to errors and more correct and whatnot, the sort of uh, the computer science world as a whole in terms of like the industry side of things has certainly not made the migration, um,
Mm.
uh, and there's probably several reasons for that. Not because like they're they're wrong or something. I don't know. It
Yeah.
just hasn't worked out, and maybe it's naive to think that. Uh, I don't know. It seems that like coping with the imperative way has made software like faster in the
Mm.
short term, and so it hasn't switched over.
Yeah,
Yeah.
that makes sense. That's very much what people were saying years ago. I wonder, I wonder what the last like 5 years of development has been, and shifts in attitude, etc. Okay, shall we leave it there for today? No, cool, no worries. And that's it for SOC for the rest of the year. Don't forget. So
Yeah.
we'll start up again.
We should have had a chance to thank you while people were still here rather than trailing off a bit. But maybe people can take the chance to thank you in the Discord or when we resume for the. You're coming back for one more lecture and then the student
Yeah,
talks,
so
right?
just think about it like we have the student talks and I'm one of the students. So I'll do my own talk and
Okay.
I'll do my modern version of monads and computer science and category theory. So I'll just present Monge's notions of computations and explain why this was significant and what the school of thought is. And that will like get the festive started, and then all of the students will come and teach us cool stuff.
Awesome. Well, yeah, thanks a
Well,
lot for this year's efforts. And I have to say, as this is the first time I'm attending as just an audience member at a class, and I enjoy that very much. So thanks, Will.
Cool. I'm glad. Okay, great. You're
thanks
welcome.
for holding the reins while I've moved across the world.
Yeah, all good. I know how hard that is. And that's when it was just me, so